Hi there and welcome from Ventura, California to today's webinar, Safety Critical Positioning for Automotive Applications, Lessons from Civil Aviation, sponsored by Novotel, Inside GNSS, and Inside Unmanned Systems, and hosted by WebAttract, the leader in educational webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the effort to develop safety standards for autonomous cars, drawing on the experience of civil aviation and meeting requirements for integrity. You'll also have an opportunity to have your questions answered at midpoint as well as at the end of the presentation during our Ask the Expert panel session with all three panelists. Now we've invited you along with over 600 professionals registered across 42 different countries and provinces representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher at Inside GNSS and Inside Unmanned Systems, would like to take just a moment to welcome you and introduce Mark Pettivello, who will be moderating the main portion of today's webinar. So over to you, Richard.
Thanks, Lori. On behalf of the Inside GNSS team, including our editor, Glenn Gibbons, and myself, I'd extend a hearty welcome to our international audience for today's web seminar. In just a few minutes, we're going to hear a fascinating discussion about how the lessons learned in building safety-critical systems for civil aviation could be applied to serve the same purpose in driverless cars. But before we begin, I just want to explain Inside GNSS's approach to our web seminars. We limit ourselves in the number of webinars that we offer each year in order to allow the time needed for preparations to ensure the high quality of the content and presentations by our panel of experts. I believe that you'll find today's event provides an excellent example of that approach. Now, I want to turn the webinar over to today's moderator, Mark Pettivello. Over the years, Mark has helped develop and moderate numerous Inside GNSS webinars, and he is especially close to today's topic. Mark's a professor of geomatics engineering at the University of Calgary. He's been actively involved in many aspects of positioning and navigation since 1997, including GNSS algorithm development, inertial navigation, sensor integration, and software development. He supervised the execution of a research contract with a major automobile manufacturer in which low-cost onboard sensors are used for centimeter-level positioning. And for 11 years, Mark's also served as the contributing editor for the GNSS Solutions column in Inside GNSS magazine. Mark, thanks for joining us today for today's event. Mark?
Great. Thanks a lot, Richard, and welcome to everybody in our international audience. I'm super excited to be part of this today. We have three fabulous panelists who bring a wealth of information to the area of safety critical positioning with a specific application towards automotive applications. So I think you guys are in for a real treat, and hopefully you learned something today that you can apply to your future studies, research, or your products that you're planning to develop. Before we get started, I'll throw it back to Lori to put together our first poll question.
Absolutely, and folks on your screen, you should see that first poll question, and we're interested to hear from each of you. When do you think fully autonomous cars will be mass produced? So you think it's before 2020, between 2020 and 2025, or after 2025? And roughly 7% of you saying before 2020, 46% saying 2020 to 2025, and 47% after 2025. So, Mark, what do you think of those responses?
Well, it seems like people have a pretty good appreciation for the challenges that go into such systems, and I think you'll actually gain much more of an appreciation for that as we go through the rest of the webinar today. So having said that, I would like to introduce our first panelist, who is Dr. Chaminda Basnayaki. Chaminda has more than 10 years of experience in the automotive telematics and V2X and connected vehicle technology development areas. He is currently the principal engineer with Renesas Electronics America, where he leads their V2X connected vehicle activities in North America. Prior to his current position, he has worked at General Motors in their R&D division, as well as their OnStar division. He is obviously very well versed in the area. He holds over 20 patents in the field and has been recognized as one of the 50 leaders to watch in the GNSS industry. He also holds a PhD from the University of Calgary, and Chaminda is going to talk to us today about his experience in the automotive industry as it pertains to the past, present, and future systems involving automotive safety. Chaminda, over to you.
Thank you for the introduction, Mark. So I'm going to talk about the evolution of automotive safety technology and touch upon some of the trends that I've seen. So let's start off with the traditional safety features that we see in almost all the cars today. Depending on which region we're looking at, some of these features are mandatory requirements. So anti-lock braking systems, airbags, seatbelt tensioning, and different forms of traction control and stability control. These are pretty much across the platform in most vehicles today. And then in some of the vehicles, we are seeing these new features coming in. Adaptive cruise control, forward collision warning, and lane keeping are some of those. And these are more function-specific automated features. So if you look at the NHTSA definition of levels of automation, these are level 1 automations. Again, these are coming in more of the newer vehicles that we see today. And of course, the next level up is combined functions, or level 2. A good example would be Tesla Autopilot. So the way to look at it would be, this includes multiple functions, combination of multiple functions. So you can think of Autopilot as a combination of automatic cruise control, forward collision warning, and some form of lane keeping, everything put together. So one level up in terms of complexity. And GM Super Cruise is another example that they claim will come out soon. And then, of course, we have other autonomous driving tests and development programs going on, like Google, Uber, and these are more limited or fully self-driving automation features, or level 3 and 4. And you will hear about these in more detail later in the presentation today. So the other aspect I want to touch upon for safety is there's convenience and safety applications that are connectivity based. So examples would be GM OnStar, Ford Sync, Toyota Safety Connect, and then Chrysler Uconnect, and pretty much all the OEMs out there got a connectivity based solution, safety and a convenience application. These are basically location-aware connectivity applications. So they have a GNSS system, the GNSS receiver that will bring in position and time, and then of course cellular for connectivity, as well as a backup source for time. And typically these systems integrate different sensors in the car. And in terms of applications that we see in these, there's standard navigation, diagnostic, prognostic functions, and maintenance functions, concierge services, and more importantly, emergency response functions. For example, if the car is involved in a crash that triggers airbags or severity that can be detected by sensors, the car can potentially generate a call, and that will go to an emergency response team with specific location and impact information. And from a customer's perspective, generally the expectation is there'll be connectivity all the time, and the device, the car, will know where it is in terms of what we call road level accuracy, or where the car is, which road it is on. Of course, there are some limitations, and generally understood limitations, cellular, GNSS coverage-based limitations. So all of these safety systems and convenience systems are typically developed on a network of sensors and ECUs, or electronic control units, in a car platform. And what I've shown here is a very simplified version of that. And you can see that there's multiple ECUs. They could be, one could be for the telematic system, one could be for safety systems, one could be for something else, engine control, and so on. And these are, along with other sensors and actuators, are connected to each other using what we call the CAN network, or control area network. The idea is that each ECU can put in information, or a sensor can put in information to that network, and other ECUs or other processes can pick it up and act upon it. So like I said, a telematic system in it will basically take information out of CAN, do some processing, and do what it has to do to control maybe interface functions or various other indicators on the cluster and so on. The connectivity device is pretty much, again, standard in modern day cars. That's a standard 4G, 3G modem, cellular modem, and that's the gateway to outside connectivity. And so this may be a part of a telematic system. This could be a separate thing. And another important aspect of this architecture is a vehicle antenna. And typically, we see multi-service antennas, meaning cellular, GNSS, XM, all of these different connectivity mediums have their antennas co-located in a single enclosure, primarily driven by styling, complexity considerations for the car platform. So this is something that you can see in most cars, or sometimes we refer to as a shark fin antenna. And this is something we will talk about in more detail later on. So in terms of challenges, the number one thing I see is whenever there's a new technology that comes in, generally that's added to existing systems as an add-on. A good example that I'm going to talk a little bit more about is V2X, or connected vehicle technology. So oftentimes there's no complete redesign of an existing car design. Instead, it will be added on. Now, obviously, for safety critical systems, there will be some redesigning needed, and good examples would be antenna, as I mentioned before. The size of the antenna, shape of the antenna, placement may need to be changed for better availability, better reliability, and so on. And of course, same goes for sensors. There's wheel speed sensors, gyroscopes, stability control sensors in a car platform today, and some of these may need to be upgraded, or maybe to have dedicated sensors for these automated safety critical functions. And if you look at current systems, specifically for GNSS, there's no requirements around reliability, integrity, or jamming resistance today. So those are things that we need to consider. And another aspect that I see as unique for automotive is that styling, cost, and complexity are very important. And the next aspect is the design cycle. Typically, a car design cycle could be as long as 3 to 4 years. And once that car is produced, service life could be 8 years or around there, could be even longer. So this is very different from a consumer device, which has a much shorter design span, design life, as well as a time to design. So there's a lot of challenges associated with this. And I think one way that the industry is trying to address this problem is to have OTA, or over-the-air upgrade capability. It is there in most of these systems, but I think there's a lot more work to be done to make it a widely usable capability for like map downloading, software uploading, especially given the considerations of cybersecurity considerations, hacking instances, and so on. So things have to be very carefully designed. So OTA capability is critical, but that has to be further improved to become useful for everything. So when we look at the GNSS technology alone, I think the industry expectation is changing, and that needs to be changed. And the reason I'm saying that is, if you look at legacy systems, we were looking at the ability to say, which road am I in? I'm happy with around 5-meter accuracy. And then with these lane-level applications, for example, lane guidance, or V2X or connected vehicles, you will need even further, better accuracy. So these will require additional sensors. So if you take the Super Cruise or autopilot examples, cameras, radars are used, and maybe even GNSS with corrections and maps may be used. So these technologies are coming in now. And then when we get to the beyond scenario, you will need even more better accuracy. And then sensor integration, I think, will be the way to do that. multiple sensors. It could be multiple technologies in the car. But one thing I wanted to point out is today GNSS still remains the only viable absolute positioning and timing source. So that still remains, especially timing, which is an important aspect as well. And I think the industry needs to see that we are going from accuracy of several meters to applications that will require centimeter level accuracy. From availability point of view, most of the time availability was good enough, and with safety critical systems you will need it all the time. In terms of reliability, failure detection is very critical, as we hear about later. So to add to this mix, I think connected vehicle technology or V2X technology will be an important aspect. This is something that's already happening, and obviously with traditional sensors there are limitations. For example, as I've shown here, sensor view can be blocked by objects, other vehicles, larger vehicles, or rain, fog, lighting conditions. So that presents a challenge, as well as predicting driver or traffic control behavior. For example, imagine your automated car is approaching a traffic light. Your radar, your cameras can see what signal phase you're facing, but that doesn't give you enough information to predict what's going to happen in 4 seconds when you get to the intersection. So you need some intelligence there, and often traffic controls are adaptive, meaning responsive to vehicles, so it's not predetermined. So connectivity or connected vehicle technology enables this information sharing. That's a key piece there, and it can address other sensor limitations like the ones I listed before. And there's a significant amount of research that has happened since 1999, when FCC allocated this frequency band for safety use in North America, and there's similar allocations in other regions in the world. And this technology is typically used called dedicated short-range communications, or DSRC. And there's established over-the-air protocols for this. And you can find out more information at this link and in a lot of publications out there on the internet. And there's industry-wide expectation that US DOT will mandate this technology starting around 2022 or soon after. And there's healthy industry discussions going on about whether DSRC is the right solution. Can we have cellular, or would cellular, next generation cellular, be the right communication technology for this? I think regardless, we will need connectivity to make our drive towards autonomous driving successful. So very basic information about V2X. So the idea is all the vehicles and pedestrians, everything will broadcast information about where they are. So vehicles will broadcast what's called a basic safety message, or a BSM. Pedestrians will broadcast a similar message, and then traffic control devices will broadcast signal phase timing information, maps and corrections, and so on. So the idea is any vehicle, any given vehicle will be able to hear from others, classify where the other vehicles are, where the other pedestrians are, and then identify threats and generate warnings further down the road, generate control responses when we get to that level. Typically, when you look at research literature and so on from the industry, you will see these accuracy levels: road level, meaning better than 5 meter absolute accuracy; lane level, better than 1.5 meter absolute accuracy. So the idea is a given car should be able to classify other objects to different awareness zones and identify threats. So a quick overview of the over-the-air messages, the basic safety message. So the idea is send this message every 100 milliseconds, use GPS time or UTC time, time mark, and then include position information, motion, heading, control status, and so on. And then there's provisions to attach additional data. For example, GNSS data can be attached in RTCM format as optional data. And these are all defined in the Society of Automotive Engineers J2735 message set. So here's an overview of the system that we've developed and demonstrate at Renesas Electronics. And you can see one of our cars. We got a fleet of 3 vehicles equipped like that, and they have sensors, traditional sensors, radars, lidars, cameras, as well as V2X technology. So this shows the engineering interface we present inside these vehicles, and you can what you can see there is input from radar, lidar, and then target classification information. And down here you can see a warning. That's a forward collision warning generated by V2X for the car that you can see in the front. So with our software partners, we enable various applications. We demonstrate various applications. And what we typically do is we have portable units that we can plug into any car, and we have DSRC enabled roadside equipment or traffic control devices. And the green arrows you see here are DSRC communication lines, so we can demonstrate how vehicles can talk to each other, and then vehicles can share information from traffic control devices. We also have the ability to have a back-end reporting system, so almost in real time we can enable a user device to show what's happening in the field. We also have the ability to, through a validated interface, put warning information. So for example, construction zone warning or hazard zone warning or speed warnings we can put in through our backend system, and that can be uploaded to a roadside unit or a traffic control device, and vehicles traveling in that region of interest will get these messages, and they will display the appropriate warnings. So finally, I would like to finish off with with kind of a challenge for the GNSS industry. So all of these connected vehicle programs are heading into their next phase. Connected vehicle pilot programs sponsored by DOT starting next year. There will be sites in New York, Wyoming, Florida, among other sites, similar sites. And this is the first exposure of V2X to deep urban canyons in a real environment. So as you can see here, this is 6th Avenue, New York. You can see the sky view is really limited. And here's a sample data set from one of our partners that shows the true path of the vehicle in green, and the output of a typical multi-constellation automotive-grade GNSS receiver. And you can see the large deviations, and this is the challenge we have. And so it's a good opportunity for the automotive industry and GNSS industry and all the experts to work together and show that this can be done. All right, so back to you, Mark.
Great, thanks a lot, Chaminda. It's obviously a very complicated and involved situation that we're trying to deal with here. I think you've done a pretty good job of capturing the key points. I'd like to move ahead now to our second presenter, Dr. Mathieu Jorger, who is an assistant professor of aerospace mechanical engineering at the University of Arizona. His background is that he has a master's in mechatronics from the National Institute of Applied Science in Strasbourg, France, as well as a master and PhD in mechanical and aerospace engineering from the Illinois Institute of Technology. He brings a wealth of experience to the panel today in the GNSS navigation and integrity field. He has led multiple research efforts on iridium augmented GPS, worked on centimeter level, carrier phase RAME, measurement level integration with laser-based SLAM, and he's currently working on multi-sensor integration for safe autonomous car navigation. He has been well recognized for his past work. He is the recipient of the Institute of Navigation's Bradford Parkinson Award, as well as the ION's Early Achievement Award. And Matthew's going to give a bit more of the technical descriptions and details associated with these types of systems. So Matthew, over to you.
Thank you. Okay, so this first slide, today I'm going to talk about quantifying navigation safety. That's the key here. And I'm going to use this acronym APV for autonomous passenger vehicles. And on this first slide, I have this illustration from a 1958 article that predicted that autonomous cars would be widely available by 1975. It did not quite happen this way, but what happened is that we saw the development of GPS, differential GPS, loose, tight, and deep integration with inertial navigation sensors. And we've had cheap or affordable laser scanners or LiDARs and radars, high-resolution cameras, powerful computers. We've had 2 DARPA grand challenges with autonomous cars. And finally, the manufacturers of major car manufacturers, they took over that idea of autonomous cars together with Google, Uber, and Tesla. And that leads us to current day. Currently, the major approaches to APVs, or the most advanced ones, focus on level 3 APVs, as Chaminda described them earlier. So this corresponds to limited self-driving automation, and the key safety feature is that the driver is expected to take over at any time. So from what we know of, the proof of safety approach in most of these approaches, the most publicized one, these approaches are experimental. For example, Google has driven 2 million miles in urban areas, which is very challenging. And for now, they have reported one collision where the Google car was at fault. That was in February of this year. And then we have Tesla's approach, who is actually commercializing its autopilot. It has accumulated 130 million miles. This is restricted to highways. And unfortunately, they have had a fatality caused by this autopilot in May of this year. So what do we make of these million miles driven and these incidents? Well, we can compare that to human driving performance. In the US, human drivers achieve approximately 1 fatality per 100 million miles driven. But that includes both recent and older cars, and it includes all driving conditions, all road and weather conditions. So it's not really comparable with the numbers we've seen before. It's not restricted to luxury sport cars that are more recent than 2011. So the bottom line here is that we don't have enough data from either Google or Tesla to either prove or disprove their safety case at this point. And we can push this argument further to say that a purely experimental approach is really not sufficient. Certainly not if we're trying to achieve level 4 autonomy. In response, what we could do as a community is to leverage the analytical methods that have been used for decades in aircraft navigation safety. And this idea has been mentioned in September of this year by NHTSA in the Federal Automated Vehicles Policy. So when we talk about aviation safety, how do we evaluate safety? Well, if we have an aircraft during an approach, this aircraft will try to predict its position close to the touchdown point, and it wants its position estimated to be within an alert limit requirement box. In fact, the probability of being outside of that predefined box is what we will call later the integrity risk or safety risk. If we want to translate that or convert it into the car problem, the autonomous car navigation problem, then we can draw a box that is pretty much limited by the width of a lane. So the first thing that is striking when we look at this is looking at simply comparing the size of the boxes. It took decades of research and considerable resources in the aviation community to reduce the size of that box to a few tens of meters, approximately 50 meters for the wide area augmentation system. That is a GPS augmentation system that was designed by the Federal Aviation Administration. And in the best cases, you can bring it down to plus or minus 10 meters around the aircraft. Of course, that's an order of magnitude larger than what we need for a car. So it's a task of epic proportion, and there are adjustments to be made if we want to convert these requirements used in aviation to the autonomous car problem. In addition, as Chaminda mentioned earlier, GPS is not reliably available on cars, so we need some kind of a multi-sensor system for navigation. The risk for an autonomous car will have to be continuously monitored, whereas for aircraft application, the risk only peaks at touchdown, so it's really only a punctual risk. So that's an additional challenge. And then we have that prediction issue. We need to predict the risk in a dynamic environment, as Chaminda showed earlier. You may have a truck passing by, occluding measurements from your laser and radar, so you have to deal with that when you're trying to predict your performance. So that makes it more challenging. Getting into more detail into the aviation safety metrics, how do we quantify safety? Well, in aviation, the risk is caused, for example, by sensor errors, and that causes ultimately a positioning error that is represented here with this covariance ellipsoid. If we focus on the vertical direction, we can plot the vertical positioning error probability distribution right here, and the probability of being outside of the box is the integrity risk, what we call the integrity risk. If we want to make a full safety case, we consider 4 safety criteria. The first one is accuracy, and that's typically a 95% requirement. So if you take a few hundreds of data points, you can prove your accuracy. In contrast, integrity is a measure of trust in the sensor information, and the most stringent requirements we have in aviation are on the order of 1 minus 1 in a billion. So that's much more stringent. That also means that now rarely occurring events that impact the tails of the distribution have to be taken into account. For example, GPS satellites are specified to have failures approximately 3 times per year. So we have to do something against that, and what we do is we detect these faults. But what is more challenging is to take into account the impact of undetected faults. That's what makes the integrity risk evaluation challenging. Then we have the continuity. The continuity risk is the risk of unscheduled interruptions. For example, we want to avoid occurrences of false alarms. So this is something I will talk about later again. And finally, we have availability, which is the fraction of time where we have accuracy, integrity, and continuity. Now we want to apply these criteria to an autonomous car navigation system. And I have represented here some of the major components of this system, including the sensors on top, together with some processing algorithms, the position and orientation estimation and integrity monitoring, and the integrity prediction. We need prediction because the risk right now is, knowing the risk right now is good, but it's better to be able to predict it so we can actually do something against a hazardous situation. So the idea here is if we have an overall safety requirement, for example, we want to do better than 1 fatality in 100 million miles driven. We can, and if we have analytical methods to analyze and quantify the integrity of each one of these components, we can allocate the overall safety requirement to each one of these components in the diagram, and we can design each one of these components for safety. And we believe that design for safety will accelerate the development of autonomous cars. Back to you, Mark.
Great, thanks a lot, Matthew. Again, I think an excellent summary of the overall challenges. And for those in the audience, just an FYI, Matthew will be continuing on with a few more details. But first, we are going to start our first Q&A session. So we've been getting some good questions from the audience, and I encourage you all to continue sending those in as we go along. I'm going to direct our first question to the one panelist we haven't heard from yet, Jonathan Auld from Novotel. Jonathan, the question is about antenna placement and size on current vehicles, and how does that compare with kind of what you need as a GNSS receiver provider?
Sure, thanks, Mark. We've seen that question commonly in our various conversations with potential customers and partners in this area. The desire for a very small, invisible, basically antenna in this situation is very high. you also have to consider that we're not trying to hit the same sort of level of accuracy that perhaps some of the higher precision applications like land surveying and such need. So we're not necessarily trying to get to millimeters or centimeters. So we have some leeway in that, but the desire, the way to summarize it would be that the desire is to have the antenna mounted into the typical locations where antennas get mounted in cars, which are sort of the rear view mirror location or the rear back deck under the back window, or the side mirrors. And in some cases, a portion of the roof panel can be made sort of RF transparent where the antenna goes. But the antennas typically are much smaller, and that drives some differences in how we have to deal with equipment and the expected performance and the materials we use in the antenna. So I think that's a good answer for that one.
Excellent. Thanks a lot, John. Wanted to follow up with Chaminda. Chaminda, there was a question. Sorry, I'm just trying to find it here. There was a question. Sorry, about V2X. You mentioned originally that there's going to be multi-sensors that are going to be required, and V2X, is it a communication protocol only, or are there some provisions for also allowing for ranging capabilities between vehicles as well?
Okay, so V2X is basically positioning capability, and it's a combination of positioning and communication capability. So each vehicle will figure out where that vehicle is by itself and then communicate information to others around that vehicle to enable safety. So that's the idea. So if you look at the technology, it's based on Wi-Fi. It's a variant of Wi-Fi 802.11p. .11p, which is a variant of regular Wi-Fi modified to minimize the handshake time between two nodes. So the idea is you want low latency, local communication between entities. So there's no ranging built into it, but there's a lot of research going on to see if DSRC technology can be used for ranging. It's not there today. So today it's basically communicate where I am to everybody else and my intentions, basically using the high-level message set I mentioned, the SAE 2735 message set.
Okay, great. Thanks a lot. I'll direct our next question to Matthew. So in your slide, you had mentioned the requirement to predict the vehicle position forward in time. And the question that has come in is, over what time intervals are you typically looking to do this prediction? Are we talking seconds, tens of seconds, minutes, or what?
Yes, so I have a colleague that looked at that and looked at the braking distance or the time to get the car to a stop, and that typically takes a few seconds, but it varies widely depending on the road conditions. If you have a slick road, icy road, it can take longer. But yeah, what I have in mind is 4 or 5 seconds as the prediction time, and so that may also play into the requirements themselves, the way the requirements are set in aviation. It actually varies widely. For en route navigation, requirements are set per hour. For final approach, it can be set per 150 seconds, which is the duration of the approach. And some of the requirements are per 15 seconds, which is the duration or the time constant of the measurement correlation. So this may have a role into how we convert the requirements from aviation to cars, or it may have a role in the requirements themselves. So that's an important number. It's something that it would be good that the community would come to an agreement with.
Okay, excellent. And actually that touches on kind of a common theme in several questions that have come in, and that's about the availability, or perhaps the lack of availability, of standards for the automotive industry. And maybe I'll throw this out to everybody. What are your thoughts on kind of what the current status is and where you see these potentially coming from and when? So maybe Jonathan, I'll throw it to you first.
Yeah, sure. There certainly isn't a standard set of standards for how GNSS or even how an autonomous vehicle system should be constructed or built to. Much like unlike the aviation world, where you have sort of the MOPS documents that say here's how you solve this problem. The way it's working right now is a lot of the OEMs and tier ones are solving the problem, or figuring out how the technology fits together, and understanding how those pieces of technology are going to have to interplay with each other, and where the error sources are, and where the tricky parts are that we're going to have to solve. There's work in all the different sensor types. There's work in the mapping world, and ultimately some level of standardization will have to come into that. In my opinion, just looking at the maps, everyone will probably have to look at a similar set of mapping data just to make sure that there's some consistency. So you can see that it's not there yet. It's coming. I guess I'd see what Chaminda's comments are on that, as to if he's involved in any of that from the SAE or NHTSA, and has any wisdom on how that development is going from an automotive perspective.
Okay, so the closest I have seen to this in terms of industry activity agreement is the connected vehicle activities. So in that, the industry has agreed, okay, these are the requirements for accuracy, for example. But I agree with Jonathan in saying that the rest of the standards in terms of reliability requirements and so on, those are not there yet. Those need to be defined. And it's an evolving thing, and it's a new thing for the industry too, I think, because this wasn't how this is not one of the things that the industry has looked at before, especially doing this sort of high precision safety functions in urban environments and all sorts of challenging environments. So there's some work to be done.
Okay, great. Matthew, anything to add from perhaps the academic side before we carry on?
No, I think this is a great topic for discussion. It could go on forever. So.
Okay. Well, in that case, maybe we will cut it short there. And before we carry on with the rest of the presentations, I'll ask Lori to conduct our second poll question. Lori.
All right, thank you, Mark. And folks, coming up on your screen is that second poll. And we'd like to hear, in your opinion, what is the most important technology in an autonomous car? And in this case, I will ask that you select your top two options. Of course, this is on the honor system, but if you could select among cameras, LiDAR, radar, GNSS, inertial map matching. 34% of you weighing in with cameras, 61% saying LiDAR, radar, 64% GNSS, 27% inertial, 18% map matching. Mark, any thoughts on these responses?
Well, I think this is quite consistent with a lot of the research and work that's being done. Definitely multi-sensor systems are going to be important, and perhaps the large percentage of GNSS is a bit surprising from my side, but maybe people know something that I don't. In any event, I think we're ready to carry on. So I've already introduced Matthew, and he's going to continue where he left off, giving a bit more of the technical details of integrity systems. So back to you, Matthew.
Thank you. All right, so I'm starting again where I left off with a diagram of the navigation system for an autonomous car, and I'm going to give you just an example to give an illustration of how we can implement these integrity and continuity risk requirements. And to do that, I'm going to talk about laser-based navigation, because it's pretty much an unexplored area in terms of integrity and continuity, the way we've been implementing in aviation. And John will talk later about the GNSS part. Okay, so if we look at laser data, you basically have a cloud of points, and each one of these points individually does not really give you much information. In fact, you have to first group the information to extract features, and then you have to associate these extracted features with landmarks that you have in your map or that you have observed previously if you're using a simultaneous localization and mapping or SLAM type algorithm. So to better explain the issue that you have to deal with in data association, I'm going to show you some experimental data that I collected by mounting 2 laser scanners back to back, so that I had a 360-degree view of the environment, and I put a GPS antenna on top to get some ground truth trajectory. And I drove that into the streets of Chicago. Yeah, the Cubs won. Okay, the truth trajectory is in red here. You can see the blue trajectory, which is the result of laser-based navigation. You can see that error growing here. This is an implementation of SLAM again, so the map of landmarks was built incrementally. Once a large error occurred, the algorithm was not able to recover. What happened here at the origin of that deviation is a case of an incorrect association. The algorithm confused the landmark on the left of the road for a landmark on the right of the road. And this is obviously a serious issue. There are many approaches to mitigate this issue, many advanced approaches. But we want to do more. We want to predict occurrences of incorrect associations. And we have developed a method to do so based on prior work in multi-target tracking. And I'm going to show you an illustration of how this works. So this is a simplified example where we use laser here in blue and GPS in yellow, and when we mix these measurements together, we have an estimate that we will represent in green. The simulation scenario, again, a simplistic scenario of a vehicle driving through a forest-type environment. GPS won't be available under the trees, and we'll use tree trunk as landmarks to navigate using the laser. So I will show you a movie of a vehicle going across that GPS obstruction, starting in a GPS available area in yellow, going through that transitional GPS and laser available area in green, and then we'll use laser only, laser beams to these landmarks, those tree trunks if you want, and we'll go out of the obstruction. You will see these covariance envelopes, or these covariance ellipses in red for the vehicle. They represent the positioning error, so this will change as the vehicle moves. And we also have covariance ellipses on the landmarks. Again, this is an implementation of SLAM. We don't know a priori the position of the landmarks, so we have to estimate them together with the vehicle position. In the upper right-hand side chart, you can see the GPS satellite. This is a sky view of the satellites. So GPS satellites that are available are in blue. The tree canopy, as the vehicle moves, will slowly cover the antenna so that all these satellites will be indicated in red. They will be blocked. And in the bottom right chart, you have a simulation of the laser-based, the laser data with some noisy measurements that are filtered out. So here you see how this algorithm works. You can focus on the covariance and the covariance ellipses. The red ellipse for the vehicle changes seamlessly as we use GPS and then laser. And the point I'm trying to make here is that, as is well known in the robotics community, this covariance ellipse does not capture all the positioning error because we have some nonlinearities and we have this issue of incorrect associations that may occur. So because of that, if we look at the actual positioning error versus the travel distance as the vehicle moves across the obstruction, that actual error does not match the 1 sigma covariance envelope. So the thick line is outside of the thin line boundary. If we represent the risk that is derived from the covariance, you can see that it's pretty low. That's the black line right here. It's below 10 to the minus 5. However, if we represent the integrity risk or the integrity risk bound that we derived to take into account the risk of incorrect associations, that risk is much higher. In fact, we have a sudden increase at travel distance 20 or 21 meters. Going back to our top view representation of the vehicle and the landmarks, at that travel distance 20 or 21 meters, landmark number 6 is hidden behind landmark number 5. And it's going to come into view of the laser for the first time at that travel distance. And the algorithm we'll have a risk of confusing landmark number 6 for landmark number 5. And this is what is captured here in that sudden increase in the risk. So we can do something against that. We can choose not to use landmark number 6 because the risk of misassociation is too high. So let's do that. We remove landmark number 6, we don't use it. And now our position error pretty much matches the covariance envelope. So that's a good indication. If we look at the integrity risk, it's much lower than it was before. But we still have a sudden increase here at travel distance 23 meters. Going back to our top view of the vehicle and landmarks, we can see that now landmark number 2 is hidden behind landmark number 5. So you may think, okay, why not remove landmark number 2? Let's not use landmark number 2. Well, the problem is you cannot just keep removing landmarks, or at some point you won't have a position solution anymore. You won't be able to continue your navigation. That's an issue of continuity risk. So we have pointed out here a key trade-off between integrity and continuity risk. Yes, removing landmarks will reduce your risk of incorrect association, but it will also increase your risk of not being able to continue the mission. This is a key point that we'll have to take into account when designing algorithms for autonomous cars. In summary, the major challenges that we've gone through here is that in order to bring aviation safety standards to autonomous cars, we'll have to establish safety evaluation methods for laser, radar, and camera-based navigation. We'll have to do that for multi-sensor systems, and we'll have to design integrity monitors. And then we'll have to predict that integrity in a dynamic environment. If we achieve this using an analytical solution, we'll have a way to set safety requirements on individual sensors. Design for safety will accelerate the development of APVs. And with these metrics of integrity and continuity, we'll have sensor-independent and platform-independent certification metrics. And that concludes my talk. Back to you, Mark.
Excellent. Thanks a lot, Matthew. So hopefully the audience has gained a real appreciation for the real challenges here. Obviously, you've demonstrated some great initial results, but obviously you've also highlighted the need for a lot more work going forward. I'd like to take this opportunity to formally introduce our final panelist today, Mr. Jonathan Auld. Jonathan holds a BSc and an MEng degree in geomatics engineering from the University of Calgary. He has over 20 years of experience in the GNSS industry, working with seismic surveys initially, and then in 1988 he has joined the Novatel team, where he has held various positions in the aerospace team, commercial development teams. He was the director of technology development and led the core GNSS receiver development team. He was the director of portfolio management, and most recently he has taken on the, I think, very formidable challenge of leading the business and technical efforts to transition their technology to safety critical markets, and obviously that's the main reason why he's here today. So he's going to give the GNSS manufacturer's perspective on this particular topic. Jonathan, the floor is yours.
Thanks, Mark. The topic here is going to be what is the industry manufacturer perspective, or at least Novatel's perspective, on how we're going to move into this safety critical world with our GNSS solution. So just a summary, Novatel is a manufacturer of high precision industrial grade GNSS solutions. We have applications in a number of different markets all over the world, and we've been doing this for over 20 years. Novatel sort of leads the positioning intelligence portion of our parent company, Hexagon, and inside that positioning intelligence group, we have ourselves, Novatel, and we also have Veripos, our sister company, that provides a global correction network that will become relevant in a few slides here. TerraStar is a brand of the Veripos company, and also we have a company down in California called Antcom that builds antennas. So from Novatel's perspective, we've been doing this for, like I said, over 20 years. We were one of the original companies that sort of pioneered this high precision technology. We see that the trends moving forward in the industry, initially starting around in the 90s, where it was all about accuracy. How do you squeeze more and more accuracy out of the system, going from hundreds of meters to tens of meters to meters to decimeters to centimeters, that kind of thing. And through that development, several new technologies were pushed out. And the phase that we see ourselves in right now is this availability phase, where it's okay you need to be as accurate as you can, but you also need to provide that solution as often as possible. And that's where adding new signals, new constellations, new frequency support into our products came about. We also moved into the world of augmenting our GNSS solutions with other sensors, primarily inertial sensors, to provide the solution in areas where GNSS was not available. And that's kind of the portfolio of products we have right now. And moving into the future, we see a future where GNSS is a critical part of these safety of life applications, where safety standards and reliability are going to be critical. And so we need to move our technology into that realm. And so that's what I'm going to talk about a bit here. Like I mentioned before, we've been talking today between Chaminda and Matthew's presentation around the automotive side of things, but there's more markets that are demanding safety for their navigation and guidance solutions. You see here on this chart a number of different markets that Novatel already provides technology into that are starting to demand requirements, and the various standards on the sides are the types of development standards you need to achieve in order to design in safety from the start. So autonomous mining, autonomous agriculture, the UAV explosion all over the world of all these unmanned vehicles that people want to use, and then railroad, and then of course the foundation where a lot of the safety concepts came from was the aviation world, where we've played a role in participating in the WASP program that Matthew had mentioned before. So how do we see GNSS fitting into automotive positioning? GNSS serves as the primary absolute position, velocity, and time generator of this solution. So you see there in the diagram that the solution is not a GNSS only solution. It will never be. It has to be a fusion solution of multiple sensors. The autonomous vehicle application is going to expect 100% availability in all conditions and locations. 100% is a difficult thing to get to, but if we're thinking about where this is going to go, people are going to want their vehicles to drive in all conditions, rural, urban areas, all weather, all visibility. All these different sensors that have to work together have their various trade-offs as where they work better and where they work worse. And so we believe the overall solution, as was mentioned previously, is going to be a sensor fusion solution with GNSS playing a critical role, but likely not the sole positioning source in this type of application. GNSS also plays a role in providing an excellent source of time alignment for all these sensors. And so from our perspective, we see the GNSS sensor as the core of this, where we can provide an absolute solution and a timing source to other sensors in the vehicle. So today, GNSS is in the automotive world today, obviously. The primary use case is driving the navigation systems that are on the vehicle for point-to-point navigation and finding out routes that you can drive the vehicle through or to. These receivers are typically single frequency, or are not typically, they are single frequency, supporting one or two constellations, tend to be accurate only to the meter level, as was mentioned previously, and have fairly low data rate outputs. The solution type that is used in these cases is primarily a pseudo-range-based solution with some carrier phase assistance for dead reckoning and those kinds of things. But the design is not at any particular, there's no requirement for any sort of functional safety standard. The GNSS isn't serving part of any system on the car that is going to have a safety of life impact. So there's no integrity data provided in the output solution. A lot of the receivers that are used, however, are built to automotive manufacturing standards. So the next bit here, this is sort of a summary of where we think, just a very high-level summary of what type of solution is going to be required in this application. As was mentioned previously, it's not going to be adequate to have 5 meters of accuracy. We need to have that sort of 1 meter almost all the time kind of accuracy, and we need that in a three-dimensional sense to deal with if the car is driving itself, to deal with overpasses, underpasses, these kinds of things. That will drive a move towards multi-frequency and multi-constellation receivers and antennas. Moving to that type of solution improves the overall accuracy, increases the number of measurements and the availability of the measurements, and will help in speeding up the convergence time of the high precision solution, which I'll talk about in the next slide. We see achieving that 1 meter 3 sigma solution as requiring a correction source like a PPP, precise point positioning service, that is available today through our Veripause sister company. They deliver those corrections over satellite and over the internet. And from our work so far in this, the rollout of this technology, as you saw with the Tesla use case, will primarily focus on highways and freeway applications, exit-to-exit kind of applications, with a transition to urban environments where some of the error error sources need more research as to how we're going to manage them and how we're going to handle these sensor fusion challenges. And then on top of that, there's a functional safety component that you need to develop these products in the context of a process or an engineering philosophy and process that drives safety into the product right from the beginning. And this is where some of the big heavy lifting work is going to be required. We need to extend the integrity analysis, as Matthew was talking about, and then we likely also have to look at authentication to ensure that the receiver can dependably know that it is tracking the actual satellites and not being spoofed or otherwise messed with. So on the positioning technology side, if we're going to have, in the ideal case, this sort of 1 meter all the time type of solution, we want to have, we're going to need some sort of decimeter level at the 1 sigma, or 5 to 10 centimeter level at the 1 sigma level to provide that. And so we believe that's the type of positioning that a PPP level of service can get to. It obviously does that today. The RTK solution that is out there is certainly more accurate, but it's not necessary at this point. If we're only trying to keep the solution inside the lane level, then PPP should be available, and PPP's infrastructure costs are lower, and we have availability over satellite for rural areas and potentially over cellular or internet connections in urban areas. So there's some backup there. So one of the challenges that is discussed quite a bit is that PPP is great, except there's this convergence time challenge that it currently takes tens of minutes for the solution to get down into that 5 to 10 centimeter level. And that is true, but there's a number of companies, and Novatel included, working to resolve that, and we expect that in the next few years that limitation will be largely removed. So the similar concepts to what Matthew was talking about, these are critical in how we're going to solve this problem. These concepts of integrity, continuity, accuracy, and availability have to be balanced and understood in an automotive use case. If we're now on the ground and we have objects above us, overpasses, vehicles driving beside us, dealing with threat models like multipath are completely different and much more challenging from an automotive perspective than from an aviation perspective. And so these concepts will have to be extended into the ground applications such that in the most basic level, the receiver cannot provide a misleading set of information. So if the receiver is providing a good solution, it needs to be trustworthy enough to say, yes, here's your answer, and it is good, and you can trust me to a given integrity risk level. And if it is not able to provide that solution, it needs to be able to provide that information as well. What you don't want to have is the receiver's output providing a indication that it is good and trustworthy when it is not. And that's a lot of the work that is going to be required to figure out how to do this in the ground application. So underpinning all of that is that you have to, like I said earlier, you have to design safety and reliability in from the ground up. It's not the case where you can just take a product and test it to these levels of integrity risk, as Matthew had mentioned. We need to design the systems, do a whole system level safety case to determine what level of reliability, the GNSS receiver needs to serve as part of an overall system. So in a lot of these cases, what happens is the overall system, the autonomous vehicle system, is declared to have a certain failure or integrity risk, I guess you could say, and then that is broken down depending on who's designing the system into how each subcomponent, be they cameras, inertial sensors, radars, lidars, GNSS, all those fulfill that ultimate integrity risk. And so the industry has, in the aviation case, these design standards of DO178 and DO254, where depending on the criticality of that system, you need to design it and have an engineering process around it that delivers the artifacts that shows that you have designed the system to that level of safety and you can prove it. The automotive world has the similar concept of ASIL levels, so that's the top line there, automotive. ISO 26262 is a similar, although slightly different standard, but there's a significant amount of overlap in how these work, and so we expect to be able to build off of our experience on the aviation side to move our processes and our development into that area where the architecture, the hardware, the software, all of that is built right from the ground up with the safety standards in mind. And in this new product or new capability, the positioning is only a single part of it. We have to have an accurate position that is also safe. And this chart here is either called a triangle chart or a Stanford chart, depending on what your background is. But this is kind of the area where these problems were solved in the aviation world. And you can see here that if you're going to have this chart here on the left of the vertical axis, you have a protection limit. So we've done some testing in our system already where we're just trying to see where are we at right now. And so at a 2-meter protection limit using a PPP solution, and this is data that's about 4,000 or 5,000 kilometers of driving, we're at a 90% availability level. So there's still some work to do if this is going to provide a higher availability level such that it's practically useful in the real use case. And then you also see that what you don't want to have is data over on this side where you're getting misleading or hazardously misleading information. And the challenge right now is to balance availability of the solution and have a probability level of misleading information at a level of 10 to the minus 6 or 10 to the minus 7 per hour. The solutions for these don't exist, and that's where a lot of the work needs to be done. And in addition to that, we think that there's a dual role here where the network, PPP correction network, will serve a function and the receiver will serve a function. But unlike the aviation world, the burden on the receiver and on the vehicle system will be much higher because the time to alarm is so much shorter. Matthew had talked about that a bit earlier, that the RAIM concepts will have to be extended into this carrier phase area for a PPP solution such that we can detect at the receiver level whether or not we have misleading information and take appropriate action. The network will also serve a purpose in there, and the work we need to do is to figure out what that right balance is as to where those have to go. The summary of the challenge. Okay, so the last slide here for me. This isn't just a matter of designing a new receiver and taking it to a test lab. We have to design it from the ground up, the receiver, the antenna, and the network to hit these safety requirements from the automotive industry and for any of the other industries. The additional challenge, of course, is the automotive world has significantly higher volumes and significantly lower cost expectations. And so high precision right now is not currently available in that cost structure, and there's a lot of work to do to bring those solutions in at the cost and volume levels that the automotive industry is expecting. Styling seems a little bit funny to put that up on a chart like this, but the antenna needs to fit into the requirements of the vehicle and still deliver the performance. We kind of talked about this earlier, that it's unlikely people will want a giant survey-grade antenna sticking out the top of their BMW. So we need to have antenna solutions that can still deliver the performance but are designed neatly and reliably into the vehicle body shape and still be able to deliver the performance. And we also need to look at our correction network, or the correction network, and figure out how we're going to design safety in from the ground up. And while doing that, we also need to accelerate the time of convergence. So you can see that this is not just a simple problem that we're faced with, and Novatel's got a team working on this day in and day out right now. So I think that's my last slide, so I'll go back over to you, Mark.
Great. Thanks a lot, Jonathan, and thanks to all our presenters today. Before we wrap things up with our second Q&A session, I will draw your attention to the fact that the PDF of the presentations will be available on the Inside GNSS website. The actual presentations with voice and everything else as well. The contact information for our presenters are also listed here, and of course once you download the slides you'll be able to access them as well. Lori, do you mind bringing up our third poll question?
Absolutely. Third poll question should be on your screen, and we're interested to hear, in your opinion, what are the biggest challenges in autonomous cars? Go ahead and again select your top two. Do you feel like it's confidence that users will adopt, sensor technology, connectivity / cybersecurity, certification, or cost? Looks like 39% citing confidence, 28% sensor technology, 58% connectivity, cybersecurity, 43% certification, and 33% saying cost. Thoughts there, Mark?
I think it's actually a pretty broad distribution, and I think that actually reflects a lot of the questions that we've been receiving. So we probably won't get to all of them, but certainly some. And I think what you'll find is that this is a very complicated topic, and there's no single silver bullet, if you will, to make it all work. So we'll wrap up today's webinar, at least from my perspective, with our final Q&A. Many of the questions I've had were directed, no one in particular, and I think many of our panelists will be able to contribute to each one. So I'll direct them initially at one person, but again, feel free to chime in if you have something to add. I'll start with you, Matthew. There was a question about the role of GNSS and how it's going to be one of the primary methods of doing absolute positioning, and the question is how do you see that happening in urban areas where the number of satellites is going to decrease and multipath is going to be higher?
Yes, as you mentioned, the GNSS won't be reliably available downtown. Whether it's going to decrease, whether its role is going to decrease, I think it's going to increase because, like temporarily, because we have new satellite constellations being deployed, as John alluded to. We have Galileo in Europe, Beidou in China, and GLONASS that has been redeployed over the past 10 years. So we have more satellites available, more direct line of sight satellites that could be used. Of course, the issue of multipath is a tricky one, and this is something that GNSS manufacturers are working on. But I think, and John and Chaminda can talk to that, the GNSS is, in my view, it's a key component. It's going to give you positioning, whether it's rain or snow, day or night, so, and it's going to give you absolute positioning.
Okay. Yeah, I think that this is Jonathan. I think that the role of GNSS in the overall solution is as one of the absolute positioning sources. There may be others, sort of along the lines of LiDAR or radar with map matching, that kind of technology. In the wide open spaces, GNSS will be great. And as we move closer and closer into the urban environment, I think the important part is that the GNSS solution doesn't mislead the other systems, and that it can be relied upon when it can't provide an overall solution. But beyond that, it's got to be a multi-technology solution once you get into the urban environment.
And
Yeah.
Chaminda, anything to add to that? Oh, sorry, Matthew, is that you?
Go ahead.
if I can just add one point, since we mentioned the maps that are needed for laser-based navigation or radar and so on. If you use a map, you need to use a map that has integrity. You need to know the integrity of the landmarks that you're using for a safety case.
And I think Jonathan made a great point in his presentation that everyone needs to be dealing with the same map, or at least need to be able to properly change between them if they're using different datums or different information. Chaminda, any perspective from your side in terms of the reliance on GNSS in urban areas? You threw the challenge out there, presumably have at least some initial thoughts.
Right. Yeah, I certainly agree with Matthew and Jonathan and what they said. So I see that this problem as just like GPS INS integration. At one point in the industry, the role of INS or inertial sensors was to bridge the gaps of GNSS and maintain the accuracy. And in this case, I think GNSS will do the same thing, provide the reliable, accurate information, and then let other technologies pitch in challenging environments for GNSS, urban environments. Now, the map or laser, radar, vision, I think these will fill in the gaps. And out of these, I think the map will be the most critical part of it. Just like Jonathan referred to before, standards, being up to date, and getting that map into the car in almost real time will be a big challenge.
And updating the map.
Exactly. Yes.
And yeah, of course, and things don't change slowly in terms of city development.
Yeah, and I was very encouraged by the responses I saw about connectivity and cybersecurity concerns as significant problems, because I totally agree with that. So collecting information about the changes in the map, validating it, putting it into a map format, getting it to cars, that's a big chain. And there's a lot more work to be done there.
Right, and that's, I guess, speaks perhaps more to the spoofing elements and not so much interference that is currently dominating the GNSS field. Would you agree?
Yes. Yep.
Yes. Okay, excellent. So the next question, Chaminda, I'll direct to you again to start, but again, everyone's is welcome to chime in, pardon me. And this has actually been touched on a little bit already, but the question is, how important is absolute position information versus relative position information in these types of systems? I kind of said that I was a bit surprised at the number of GNSS responses in the second poll, and again, I thought more people would lean towards the relative side of things, and I kind of want to hear everybody else's thoughts on that.
Yeah, you're right. There's some thinking that relative navigation positioning can do some of these autonomous functions, and I think we need both absolute and relative. And the requirement on the absolute side can change depending on what other sensors we have, what other information we have. So this, going back to the previous answer I described, so if you have a very accurate, up-to-date map, and if your sensors can pick up enough points of interest that can be matched in that map, then of course you can do relative navigation. But here we are not talking about just limited spaces. We're talking about vast areas of cities and maybe countries. And to get that kind of very accurate information, map information, and have enough sensor capability in vehicles to detect information out there and do the matching of those features, that's a big challenge. So I think that's where GNSS can help. So GNSS can pretty much in all the environments can identify an absolute location to a certain degree of accuracy, and then the other sensors or other information that we have can be used to refine it. That's how I look at it, that problem.
Okay.
So
this is Jonathan. I think the other piece is that maybe not on the autonomous side, but on the connected side, when vehicles will need to provide an absolute, very accurate position to each other in situations where they may not be able to visually pick each other up. In which case, you could do it with, if you could see everything, you could do it with some of the other sensors. But in cases where they can't pick each other up, blind corners, these kinds of things, there's still a need for an absolute positioning source that could be transmitted between the vehicles.
Yeah, that's an excellent point.
Definitely.
Matthew, anything else to add?
Yes, I guess I would classify these kind of broadly as the idea of going from point A to B as a navigation problem which needs absolute positioning, and the problem of obstacle detection as being a relative positioning problem. You know, you don't want to run into the guy in front of you or in the back or in a pedestrian and so on. So this is kind of how I look at this. I think the map can be connected to an absolute reference frame, but there are other things on the roads that you have to deal with relative navigation, with obstacle detection systems.
Okay, excellent. So clearly not a straightforward problem indeed. John, I'll direct the next one to you. It's actually, I think, very much related to what was talked about just a second ago, but that's relating to the absolute source of time. Do you have any feel for what the required accuracy and or integrity needs are for that? And Chaminda, I know from your perspective, you may have some comments on that afterwards.
I do, and unfortunately it's not on the top of my head right now, but I see Chaminda. Yes, I do, but I would need to open up some documents and take a look. So maybe Chaminda has that on the top of his head.
Yeah, so the only timing accuracy, not integrity, accuracy requirement that I've seen in a published standard is the V2X SAE minimum performance requirements, SAE J2945/1. I know it's a long name, but we can probably add that to our reference list after. That specifies 1 millisecond or better accuracy for V2X communication. So when you're time stamping the vehicle location, motion information, that time has to be accurate to 1 millisecond. So that's the only requirement I'm aware of. There's probably a lot of research going on.
The integrity side of it is the part that needs to be developed as to how well you can trust that timing accuracy. And there are answers to that question, but it's still a work in progress.
Agree.
Okay. Matthew, anything to add from the timing side?
No.
No. All right. In that case, you'll get another question instead. So this one, very interesting question, I think, and it's with regard to integrity. Do you think there's a need for multiple receivers for redundancy, for accuracy improvement, potentially to mitigate the effect of jamming and spoofing?
Yeah, I guess for integrity, I mean, if we want to design a system to the 10 to the minus 9 risk level, I don't think that we can build hardware to achieve that level of reliability. We have satellites in space that cost millions of dollars, and they do fail once in a while. So we have to acknowledge that. We have to be aware. And if we want to achieve a decent enough mean time between failures, we may need redundancy in the receivers themselves. Now, I guess there is a cost question, whether it's more expensive to have 2 cheap receivers that combined with their independent failure achieve a decent mean time between failure versus having one very reliable receiver that may be more expensive than the 2 cheap ones. So maybe John can talk about that.
I think there's a couple ways to answer that. There's Matthew kind of summarized it, that when you break down the failure rates of all of these, you can come to a conclusion that, well, we need to provide a redundant receiver, but a lot of the resistance to that is obviously size, cost. What do you do with another antenna? These kinds of things. So the ultimate idea is that the GNSS is part of an overall system, and that other sensors may take up some of the risk when the GNSS can't, given that it achieves a certain level of reliability.
Okay, great. And I think just to wrap it up, we'll ask one. I'll focus this one on Chaminda. Others are welcome to chime in. Do you think that a vertical protection level is really necessary for automotive applications? And if so, why or when?
I would think it will be necessary, but not as critical as the horizontal domain, obviously, because of the degrees of freedom around a car. I think it will be required because you'll have to deal with bridges with multiple decks or overpasses, underpasses, those situations. So it will be required. That's what I think.
Anybody have anything to add before we sign off?
Nope.
Hearing none, I would like to thank our panelists for their excellent presentation and their ability to answer some very difficult questions, I think, in some cases. And thanks to the audience for attending. And Lori, I'll turn it back to you.
All right, thank you, Mark. And before we sign off, again, thanks everyone for joining. Trust that you found today to be of value, as well as special thanks to our distinguished panel members, of course, our sponsor, Novatel, and co-hosts Inside GNSS and Inside Unmanned Systems. Again, thanks for joining. This is Lori Dearman saying, hope we see you on the next one. Bye for now.